Okay, so welcome to the test and validation session in the afternoon. I'll be testing system chip built in with chiplets. I'm Rajesh Pendurkar, and here's the list of the people who contributed this work. So the outline of the talk today is I'll be talking on a higher level system in a test problem, system in a package test problem, and focus on the key issues, especially the increasing test insertion steps going from monolithic as opposed to the system in a package. So I'll basically distinguish between the steps. And secondly, of course, we have to have this important requirement of KGC instead of KGD. I'm just changing the name to KGC, which is known good chiplet. And then I'm going to, for the purpose of this talk, going to focus on two very important aspects so that we'll cover. This is a big topic, so we need to focus on some important topics in the coming future. That is a thermal profile and interconnect test. And then I will give you the overview of DFT architectures and what are the standards, especially the IEEE standards, which we can be used very effectively as a solution, and then we conclude. So as you can see, right, segments like consumers, automotive, high performance, HPC, especially AI/ML applications is exploding the multi-die requirements. So consumer appetite is increasing, so is our chip sizes. And we are reaching the reticle limits. So we need to understand why system on a package is becoming now a way to go. If you see the theme of this conference is design, test, and build at scale. And that's what I think every major promoter of this conference is talking about. However, when you build the system on a chip, any one bad chiplet or die will cause the whole package to fail. So we have a lot of challenges to solve. First of all, how we build a cost-effective system in a package. Especially going forward, we have a future that a open chiplet economy, which is also promoted by OCP, is going to be the reality. So if the chiplets are coming from different vendors, how do you get a good system in a package? And how do you guarantee the structural coverage, like interconnect test and solving the structural faults? For that, we need to guarantee we have a known good chiplet, because that is going to finally lead to known good stack, which is like you are building a system in a package using advanced packaging. And can we reuse the chiplet level test at the system level? And then how do we transport the data from chiplet level test data to the final product and exercise repair? Because repair is going to be very costly to get the yield back, assemble yield back. So here is a quick overview showing you the 5.5D design. On the left side, you have HBM stacks. So they are actually very mature technology. And on the right side, actually, you have 2.5D, but on the top, we see a lot of memory chips to stacked on top of each other to increase the performance. Now, on the top right, we have the fundamental justification on why are going chiplet-based design, right? Why system on a package? Because as you can see, as we are reaching the reticle limit, we cannot basically manufacture with a reasonable yield to get economic feasibility. So we have to go and dice the big SoC into chiplets. So you can get 20% yield improvement as shown here. What is not reflected here that we get a 20% at the cost of increased test, because now instead of having one SoC to be tested, we have to have 4 chiplets tested. So you increase the test time. However, it is an economic justification that test cost for testing 4 chiplets, since they are smaller, will be accounted for in the increased advantage of 20% yield. And you can see in the picture above that when you go 2.5D and 3D, you need to also account for those TSV structural tests, because they can be shorts and opens, especially going for micro bumps. The probability of getting them defect free is definitely less. So these all adds to the cost. So what used to be a monolithic IC, the equation was very simple. Now we have to have a chiplet cost model, which is you have to have n number of dies. Every die has to go through a test flow, then packaging, and then assembly, right? So let's take a deeper dive into test costs. So top chart is very simple. You go through this typical monolithic design, and linear increase in the scrap cost, because if there is a problem, definitely you are going to lose some yield and will not get final, you have to throw some dies. However, when you come to the bottom flow, we are having a number of insertions. Since now this test system in a package is going to integrate multiple dies, and that dies may not be same, right? You can integrate various dies. That's why it's called heterogeneous integration. So they will go to each flow, and finally we have to have two things. We need to guarantee the known good chiplet pre-assemble, and then we go to the assembly. We need to guarantee that we have known good stack after the assembly. So if there is any problem, we need to have a mechanism to either repair after the assembly, because it is very costly. So the cost is shown in the right side. It is going to go exponentially high. At the same time, we need to guarantee that whatever you do at the chiplet level, we need to be able to seamlessly transfer those pre-verification patterns, maybe characterization patterns, timing patterns, all the way to the system level. Currently, all the manufacturing tests at the system level get transferred, but we are limited by the test ATE power. Automatic test equipment has some power limitation. So we have to guarantee that system level test, which is run in high volume manufacturing, is also applicable to system in a package. And it has been shown by established tester companies like Teradyne, Advantage, that SLT does catch some of the faults which are not detected by structural tests. What I mean by structural test is defects due to silicon manufacturing. So now here is a quick comparison of what we are talking. What I'm going to bring your attention to is when you go from typical monolithic test flow versus system in a package, we have seen a flood of test insertion increasing, as you can see earlier in the equation, in number of dies in the cost model. So these test insertions will vary depending on which die you are going to integrate on the system, right? Memory die will give some different qualification. Logic die will have different qualification. So as you increase the test insertions, definitely you are going to face more test time, and more test time is going to directly proportionally increase the cost of your package. And one thing I would like to emphasize here is when you are building a chiplets, not for monolithic application, but for a system integration, it is desired that you stress that chiplet much more than a regular die, which is going to be packaged as a single package. Okay, the reason is thermal variation, power noise, and other factors. Because a single die, when packaged in a single package, is going to be going through a very, very different system stress when it goes on a PCB. This package, advanced package, especially going to different scenarios. So, what are the challenges? I would like to bring to attention the thermal and challenge and interconnect test challenges. Some of the very important for getting the system in a package assembled yield to be at a reasonable economic viability level. So, what test does? Test exercises some local logic, and that is maybe different from your functional workloads. So, functional workloads are distributed as far as stress is concerned. So, test actually exercises in a very rigorous fashion. So, definitely your temperature stress is going to increase, and that cause local hotspots. Now, packaging characteristics also will be affected because there is hybrid bonding, all that stuff. The way warpage is going to happen, there is a mechanical stress. And then, if you go back to the chiplets, we are to also focus on what is the layout and floor plan to make sure that in the system level, that is not causing a thermal problem. And in final, we have to also look into the system lifecycle management because some of the latent defects which goes into the product, we are not going to catch it unless something goes wrong way in the later part of the cycle after 5 years. And some of the silent data corruption type of faults, we do not know what's. So these are precautionary important things we have to take at the chiplet level when you go from hierarchical design. And second is very important, interconnect. We are building now three-dimensional stacks using TSVs. And especially now microbumps has now gone to hybrid bonding, which is, I think, at the order of 2 micrometer pitch. And you can imagine how complex that process is, that if there is a particle, it's going to affect more balls than compared to micro bumps. So this is that kind of defect is going to make the entire cluster useless. So we have to have a spare stuff. So that is called repair. So to go further into structural side, right, we can definitely do something as a design level, like some pattern delivery of structural patterns, which are definitely different than the functional patterns. Then especially in the multi-core chiplets, as a test, they do not understand functional level. They just wanted to reduce the test time. So we, as DFT engineers, we try to exercise all the tests in parallel, and that is going to cause high di by dt. So we need to have a staggered bring up of all the scores. And also the physical design team needs to understand that this PDN, like power distribution network, is basically addressing these issues, especially going on. And then ATE is definitely has its own limitation, although there are functionally a lot of power throttling features are there. You don't exercise that on ATE. So steps are, especially I'm going to focus on the two approaches, which is a structural test using scan. Either you can do staggered at-speed, because at-speed test is a must these days, is all these clocks frequencies going up. So either do staggered clocking, and low power ATBG is every major DFT tool, CAD vendor is supporting this. So low power is like how do you reduce the activity at the output of each storage element like flip-flop, and you can just reduce when you are shifting. And shift power is also very known to be having a big power consuming point. And second is layout aware, because if you are going to add some DFT structures, especially compressor and decompressor, which is a state of the art. We have to do it in today's complex chips. You make sure that they are layout aware, so there is no single location where you put all the DFT logic and distribute it, and make sure that you do not have local hotspots. And for power and temperature monitors, which are basically important for sensing, especially you're running the gigahertz ARM core or something, then you need to sense it, and those sensors need to be distributed all over the chiplet, and they can be definitely integrated into higher level system and package level access, because if you are using IEEE 1687 standard, which is like an embedded instrumentation, so that is one thing IEEE has mentioned. So all these standards are mentioned here. So they help us make our chiplet testable all the way to the system level, and especially if you look at today's world and today's test community, everybody is interested in system test and how do you exercise all those patterns all the way from in the system using the box created by the Advantage or Teradyne. They have a way to run our CAD patterns. So hierarchical test is a must, and mentioning all these standards, I would like to bring you to your attention the two standards, especially for UCI standard. There are some of the standards are already used, and for HBM, if you want to build a HBM stack, this IEEE 1500 is a core level standard. Also, it was defined a way earlier. It has been adopted in HBM. So this is showing how you can go up the stack, send the test stimulus up using parallel, and get that response down at the bottom die, which is talking to the outside world or the PCB. Okay, so this is just summarizing all the standards. P1500 is used in HBM, and 1838 is another standard, which is basically testing the stacked ICs, and now it is being powerfully used in all the 3D ICs built by all these big hyperscalers. And then finally, the interconnect test is important because we are talking about hybrid bonds, 2 micrometer pitch. There's definitely going to be, as I mentioned earlier, big particle causing shorts, and shorts are more common than opens, but we need to basically fix and repair this interconnection. So UCI has 3 standards anyway. For A for advanced packaging, S for standard packaging. And finally, it has also the standard for 3D. So it uses 1838 standard. So finally, accelerating the test cost is basically summarizing whatever I have mentioned right now, is we make to sure that we have a known good chiplet before the assembly. And after the assembly, we need to guarantee that even the entire stack is defect-free. So we do need to exercise all the possible DFT architectures and as well as the standard and make it interoperable. That is the important thing, because if you are going to work with different vendors and you are a package integrator, it is up to you to follow up with each chiplet supplier and ensure that they follow the standards. So that otherwise you will get handicap that some chiplet vendors are not adding 1687 just for some reason or the other. So that's the conclusion of my talk today. We talked about 2 thermal challenges, especially system and package power. Actually, whole conference I'm hearing power in a different sense, and I'm here talking about power in a test sense, because yesterday there was a panel and everybody was talking about power. Here, at least I have not talked about even integrating optics. That's another big challenge for test. So we have to make sure that we address those challenges right in the design stage, and DFT and IEEE has good standards in addition to JEDEC, of course. And hierarchically, we can make sure that those qualified chiplets are qualified way earlier. The integration will be smoothless. And last thing I wanted to figure that IEEE is already understood this importance of interconnectors, and P3405 is the standard we are working on. Thank you.
Hello, I had a quick question. You briefly alluded to some power challenges in ATE that leads to SLT. Could you quantify those?
I don't have the quantification numbers, but the test, whatever verification test, silicon verification test we are putting to silicon level, they will be limited to the ATE power number. So
yes, I understand.
Yeah. So
my question is there a fine line beyond which it is SLT versus before that it's ATE?
Okay, so that number actually I don't have right now, but
Okay.
that's a...
Where do you make that decision point is the question, but okay.
Okay. And another thing is SLT also needs to reproduce the functional workflow, and that is not happening. Because, of course, Teradyne, I have produced the data. I was attending ITC. Oh, you are Teradyne? Okay, so you have actually proved that SLT is so critical for finding the last-minute escapes which are not caught by structural test. Thank you.
Parallel chip test at chiplet. So if there are hundreds of chiplets, how would you enable parallel chiplet test?
So that is right. Actually, when I say parallel, it is that is sorry, I'm out of time. But one quick question is there is some EDA companies have internal structural scheming sort of network defined, or even fabric tests that can be done, and depending upon the power profile, you can run compression patterns inside chiplet.